Good evening, everybody. Uh, we are going to discuss about the techniques of land leveling, particularly involving the plane method. As usual, let us go for our presentation. Now, I am covering only plane method. There are several methods, of course, here. Already we have covered these slides, I think, earlier. Up to criteria for land leveling. Now, yeah, plane method of land leveling. Actually, there are several methods. In fact, the basic methods of land leveling design are one is a plane method and a profile method, plane inspection method, contour adjustment method. I'm not covering all these things, but the important one is a plane method I am covering now. So each method has its advantages and disadvantages as usual, and is best adapted to specific site conditions. The plane method is the most commonly used method of land leveling design. Its use, however, is restricted to those fields where it is feasible to grade the field to a true plane. The following is the procedure for land leveling design. First, to determine the centroid of the field. So normally this plane method is restricted to the fields where the field can be made to a certain slope or simply a field. That's all. Normally in all these cultivation methods, it's a leveling or to a certain slope is good enough, unless it is a somewhat undulating and other things. So that's why if you learn this and other things you can learn on in bone. So in this you have first thing is to determine the centroid of the field, and also next average elevation of the grid points. So let us have theoretically how the procedure is, and one example we will take and then try to determine the centroid of the field. The centroid of a rectangular field is located at a point of intersection of its diagonal. For example, you can see, suppose this is the rectangle. Okay, a little bit hand drawn, not so good here, but if it's a rectangle, where is the centroid is located? You can connect the opposite corners like this, and where they get intersect, then that is the centroid. Similarly, the centroid of the triangular shape, where you get centroid from the half of the one side of the triangle to its opposite vertex, you connect. Then if you are going on connecting like this from this is the side, one side of the triangle, half of it here, and connected to the its opposite vertex like this. From here is the half, connected to the opposite vertex. Here is the half, connected to the opposite. They all get intersected at one point, that is called centroid. So for regular shapes, there are some methods like this, but irregular shapes, how to find out the centroid is a some kind of the problem. So the centroid of a rectangular field is located at the point of intersection of its diagonals. The centroid of a triangular field is located at the intersection of the lines drawn from its corners to the midpoints of the opposite sides. So that is okay for these are all regular shapes. Whereas how to find out the centroid of an irregular fields, that is now we are discussing. The area is first of all divided into, for a irregular field, the area is first of all divided into rectangles and right angled triangles. This is the one thing we must do. The centroid is located by computing moments about two reference lines at right angles to each other. This actually practically we see how they are done with an example. What is that? First thing, the field has to be divided into various rectangles and triangular pieces, and then the centroid is located by computing moments about two reference line at right angles to each other. Let us see how they are done. This is a example taken. This is not a a triangle or rectangle or other thing. It's this corner has been cut, so it is considered as a regular field, and this field is divided into a grid. You can see each point at this point location. You can see 12.5. It represents the elevation of 12.5 meters this side, 12.5 meter this side, 12.5 meter this side, like this. 25 by 25, it represents this elevation. So we have selected two reference lines. This is the one reference line along x direction. This is another reference line along x direction. The lines on this line, it is called 1, 2, 3, 4, 5, 6, 7, 8, 9 numbering, line numbers. On this y direction, A, B, C, D, E, F, G. So for a particular elevation, we call D and 2, D2. This point is D2. So like that, all this field is divided into like this. This is a grid form. These are the elevations. You can see you have taken the elevations. So then let us see the procedure. Now what is the procedure is, for example, this is the line you have selected, A, and the line A from the reference line, this line A having a distance of reference line 12.5 meters. Let us go back. You can see this is the line A, which is having from reference line 12.5 meters distance. So how many points are there? Stakes. We call it as a stakes. 1, 2, 3, 4, like that. There are 9 stakes. 9 stakes. So there are, the line A is at a distance from reference line is 12.5 meters. This is all in this distance is in meters. Of course, we should have written here computing moments about reference line, distance in meters. You should have written meters here. Okay, so 12.5 meters distance, line A, and along that line you have a number of stakes 9, and 9 into 12.5, this is the product. Likewise, line B, let us go back. Line B also same, 9 stakes are there, but line B is at a distance of this 12.5 plus this 25 meters, because this grid is 25, no? 25 plus 12.5. So that is how it comes here, 37.5. Number of stakes is 9 as usual in the line A, and this is the product, 337.5. So like that, line B, line C, line D, line E. Of course, in the line F and line G, number of lines F and G, the number of lines are coming down. Here is a 7, here is a 6. So like that, the products are computed. Number of stakes into distance from the reference line. What is the reference line? You can see this is the reference line here. This line is the reference line. So then what is the next step? The number of stakes are 58. You have to add all this number of stakes. And similarly, this product is to be added. So when you are adding all the number of stakes and the product totals are done, then the distance of the centroid from the reference line is then obtained by dividing the sum of the products by the total number of the stakes. Just now you have seen this is the sum of the product and these are the total number of the stations. This product divided by this total number of stakes will give you the distance from the reference line where the centroid is passing. That line only it will give you. So let us see what is the value you got when you are dividing 81.896 meters. So let us go back. 80, this is the, so from this reference line, you can see we are computing movements from this reference line. So it is at a distance of 81.896 meters like this. In this line it may be there. So similarly, if you compute movements with reference to this line, then you will get one more line like this. So you got this line at 81.896 from this x-axis you got. Similarly, you can compute from ABCD line the movements. You can get another distance. So another line of reference may be assumed at 12.5 meters to the left of line 1, and the location of the centroid in the east-west direction is computed as 105.63 meters from the reference line in the same way. Again, I repeat, in going back, you can see, so this is the reference line which is at 12.5 meters from line 1. Okay, so when you are go on computing, you are getting this procedure, repeating that procedure, and you are getting this distance. This line you are getting around 105 point something. Okay, so earlier line, this one, sorry, this one 106 point something, 105 or whatever it is. So earlier you got this line, now you got this line. Both are getting intersected at this point. This is called centroid. So let us go there. So another line of reference may be assumed at 12.5 meters to the left of the line, one, and locations of the centroid in the east-west direction is computed as 1.5.603 meters from the reference line in the same way. So with 2 dimensions, the centroid point is located. So that is, the coordinates are 105.603, 81.896. So these are the coordinates of the center. This is how the centroid is determined. Now, determination of the average elevation of the field. So this is obtained by adding the elevations of all the grid points in the field and dividing the sum by the number of points. You can see, again, go back. So this is the centroid. Okay, we got by the intersection of this line and this line, which are computed movements. But there are number of these elevations are, you can see, at each and every place. There are, how many places we have computed? There are 50 earlier stakes we have seen, 58 places we have computed elevations. So this is obtained by adding the elevations of all the grid points. These 58 elevations are added, which is coming to be 99.48 meters divided by this 58. So 99.48 divided by 58 gives you 1.75 meters. This is the average elevation. These are the two things. One is the centroid of that irregular field. Another thing is the average elevation. Now the concept is, any plane passing through the centroid at this elevation will produce equal volumes of cut and fill. If an imaginary plane is passing at this elevation from the centroid, will cut that field into, it produce equal volumes of cut and fill. At one place it will cut, another place that cutted material can be filled. So this is the concept. So what is that? Any plane passing through the centroid at this elevation will produce equal volumes of cut and fill. That is the concept. So with the elevation of the centroid known and the downfield grade or slope, downfield slope or grade, and cross slope selected, the elevation required at each grid point can be calculated. You can introduce slope also here, which direction you want to introduce slope. Accordingly, you can add the material or you can fill the material. So that is how a required grade is prepared. If you feel you want a required grade, you can prepare. The desired cut or fill may be computed from a comparison of the original and the proposed elevation. You can see the balance sheet where the material has been removed and where the material, this cut must be equal to fill. This is how it is checked. So we will stop this video here and we will verify this method with an examples. Thank you very much.